Well, tonight our topic is definite integrals with U-substitution. And it's not going to be too overwhelming tonight. But there's one thing we need to put in our notebook here. We're going to need to start and be very, very clear about this all night. Keep repeating it to yourself. Everything, okay, and I mean everything, must be in terms of U. And let's put another little asterisk next to that. And I'm specifically talking about the bounds. Okay, and that's going to be our big catch tonight, is everything needs to be in terms of U, specifically the bounds. Now, I know you might think this is tedious, but we are going to copy down these directions. There's a few extremely important steps that are going to be brand new here. So it's going to start very similar to yesterday's rules. Number one, we're going to set U equal to the part of the integrand, usually a function inside of another function. All right, so we basically have to pick our U. Step 2, find du dx and solve for x. Step 3, substitute the expression found in part 2 for dx. Okay. 4, simplify the integral so it's in terms of u. So basically, up until this point, this is what we've talked about yesterday. Okay. Now here comes the new part, and probably the most important part. You need to convert the upper and lower limits in terms of u. Then you integrate in terms of u, and evaluate the definite integral using the new upper and lower bounds found in step 5. So again, pause it, take a minute, copy that down, and then we'll dive into our first example. All right, we're ready to dive into problem 1. We'll go nice and slow. A lot of the steps will be similar to last night, and then we'll just really, hone in on those u-bounds. So the first 4 steps that you just wrote down are exactly what we did the night before. So let's go ahead and pick our u. Remember, it's the function that's inside something. Okay, so nice and neat. U equals x squared plus 1. We'll take its derivative, so du equals 2x dx. That gives me du over 2x equals dx. And in my head, I'm doing a mental check. Is that 2x going to cancel with something there? Well, certainly those variables disappear, and I don't care about constants. That's fair game. All right, so now we'll take this and we'll substitute it into dx. So I'm going to get the integral of x. This chunk is u to the third, and then I get du over 2x. Okay, notice I didn't put any bounds on there, and I'm going to talk about why in just a moment. Those cancel. Pay attention that 2's on the bottom. If you're dividing by 2, that's really a 1/2 we're multiplying by. U cubed du. Okay, now, we started that, asterisk in the beginning there. We said we really have to be careful about our bounds. I want you to be very clear, and I want you to go back, and I want you to circle these bounds, and I want you to make a note that those are in terms of x. And how do I know that? Well, x is the variable in the problem. Those bounds only go with x. My function is u, so you have to create new bounds, and it's very simple. Let's start with our lower bound. Okay, if x equals 0 is my lower bound, I just plug that into my u. So I would say u equals 0 squared plus 1, u equals 1. That is now my new lower bound. Let's go get our upper bound. That was x equals 1. So I let x equal 1, plug that into my u function. U equals 1 squared plus 1, u equals 2. That is now my upper bound. Now, let's make a note. I officially have bounds in terms of u. Okay, and that's the whole key to u substitution with definite integrals. The bounds have to be in terms of the function. Now, it's very simple. We just go ahead and integrate. We get u to the 4th over 4. I got my 1/2. Remember, there's no plus c when we have bounds. We draw that vertical line, 1, 2. And we're just going to substitute this in. Now, remember, that 1/2 is times that, so I'm going to leave my 1/2 out front. And I'm going to substitute in the 2 first. So I get 2 to the 4th over 4 minus 1 to the 4th. Obviously, 1 to the 4th is 1 over 4. I'm going to clean up inside and then multiply by my half. And again, that's just a personal preference. So I've got 1/4, 4. That's 2 to the 4th is 16. So I've got 16/4 minus 1/4 gets me 1/2 times 15/4, or 15 over 8. And that's it. We've integrated a definite integral with u substitution. Now, let's quickly talk about the bear trap here. make sure, and you got to keep talking to yourself, that self-conversation you have, the bounds have to be in terms of u. All right, that's the whole key. The bounds have to be in terms of u. Let's try another one. All right, so we're ready to dive into example 2 here. Now, let's first take note of the bounds. Are they in proper order? And that's the first thing that needs to go through your head every time you see a definite integral. Are my bounds in order? They are. We're in good shape. What I want you to do is I want you to do the complete u sub, where you write this expression in terms of u, and you change the bounds. Okay, now don't cheat yourself. We want to get good grades on our test. Make sure you're pausing and doing this when you're supposed to. Pause it, see what you get. All right, did you get what I got? Hopefully your u sub was easy. We picked the function inside something. Notice its derivative should be du over negative 38. Substituted that in, so I pulled out that 38's on the bottom, so I'm pulling out a negative 1 over 38. Now I'm going to go get those bounds. I have to change my bounds. These bounds go with the letter x, and I know that because this says dx. I no longer have dx, so I cannot use 0 and 1. I have to get u bounds. So I said if x is 0, plug it in to get my u. 27 minus 0 is 27. That was my lower bound. If my upper bound was 1, substitute that in and I got 8. Now we've got one big problem. Is your gut telling you something's wrong with that integral? Hopefully. The bounds are in the wrong order. So I do have to switch them if I want to move the 8 and the 27 to make sure my lower bound is the low number and my upper bound's the high number. I do have to now make this a negative, which will, in turn, make it a positive. So I am integrating. I have 1 over 38, the integral of 8 to 27, of u to the 1/3 du. Okay, again, I had to switch my bounds, so I had to make this term negative. All right, let's go ahead and integrate real nicely. I'm going to add 3/3, so I get u to the 4/3 times 3/4 from 8 to 27. Okay, so we're leaving it in terms of u, and don't forget you have that 1 over 38 out front. Now here's what I like to do to make my mental math easier. I'm going to multiply these front terms and say I have 3 over 152 u to the 4/3. And I'm just going to carefully substitute. I'm going to leave this fraction as like a coefficient out front, and I'm just going to carefully substitute those numbers in. So I'm saying I have 3 over 152 times, so I'm using my first fundamental now, the integral of the upper minus the lower. I'm just going to write it down, and then I'll evaluate it. 27 to the 4/3 minus 8 to the 4/3. All right, so lots of mental math. None of this will be calculator active. Okay, when you have fractions, the root goes on the bottom. So it's the cubed root of 27, which is 3, and 3 to the 4th is 81, minus the cubed root of 8 is 2, and 2 to the 4th is 16. And don't forget you have that lovely 3 over 152 out front. If I subtract those, let's see, I think I get 65. Oops, so I have 3 over 152 times 65. Okay, put that over 1 if that makes you feel better. And that leaves me with a total of 195 all over 152 for my final answer to that definite integral. All right, so there's a lot of mental math, which we got the other day from U-substitution, but our big goal is to watch those bounds. All right, example 3. Now, you might be a little intimidated right off the bat because you see this radical 5 here, but remember, that bound goes with the letter x, and you probably won't end up using that if we need U-sub. All right, so my first goal, check those bounds. Okay, low bound, high bound, perfect. Do I need U-sub? Do I have a function inside of a function? Well, sure I do, right here. And mentally take its derivative, okay? We should be, smart enough now to say, if I pick that as my u, is its derivative going to cancel with that guy? Well, what's the derivative of x squared plus 4? 2x. And my x's will cancel. All right, so let's go ahead. Let's do our u-subs to do the same thing. Do the u-sub, change the bounds, pause it, and see if we get the same thing before we integrate. See you in a few seconds. All right, you can take a look at mine. Hopefully it matched up. Again, the u is the function inside something. So I had its derivative as a positive 2x, so du over 2x. Substituted in here, you can see. The x's cancel, that was the whole point. The 2 is on the bottom, so I'm pulling out a 1/2. If I said x was 0, I got 4 for a lower bound. And if I said x is radical 5, I ended up with 9 as my upper bound. The square and square root obviously cancel. The last thing I'm going to do is rewrite that one more time. Okay, I don't like how it's written. Remember, the power rule says you have to have a variable to a power. So I'm going to say this is u to the negative 1/2 if I want to bring it upstairs, du. All right, so let's go ahead and integrate. So I get u to the 2 over 2 gets me a 1/2 or times 2 from 4 to 9. And don't forget you already have a 1/2 out front. So I'm going to multiply those together first, which is very handy. Those just zap out, cancel to a 1. And look how easy this is. I basically just have integrate my upper minus lower. So I've got 9 to the 1/2 minus 4 to the 1/2, which of course is the square root of 9, which is 3, minus square root of 4 is 2. So I get a nice rosy answer of 1. Alright, I read your mind. I was thinking you were saying spice it up with some trig, so let's go ahead and do so. And again, I think the u should be obvious. It's always that function inside something. So I'm going to say let u equal, and again, just use some common sense, guys. What fraction, when you see a fraction, okay, it's really a number times t. I'm saying this is pi over 12 times t. All right, let's be smart when we rewrite things. So I get my du is just pi over 12 times dt. All right, now again, be smart. Don't divide by fractions. To get rid of fractions, multiply by their reciprocals. Okay? Multiply by the reciprocals. So I get 12 over pi du equals dt. All right, so I'm never dividing by a fraction. I'm multiplying by its reciprocal. So let's rewrite this pair. I'm going to get the cosine of u, and in place of that, I'm putting 12 over pi du. All right, bounds. Let's see. If I plug a 4 in for my lower bound, I get pi over 12 times 4, which is going to turn into, 4 pi, it's going to turn into pi over 3. And I'm going to take the upper bound and plug it in. So I'm going to say u equals pi over 12 times 6, which will turn into pi over 2. All right, now slow down. You still have to check to make sure those bounds are in the correct order. Pi over 3 is 60 degrees. Pi over 2 is 90 degrees. Of course, I'm in the right order. All right, so I'm going to rewrite this one more time so it's nice and neat. I'm going to pull that coefficient out front. 12 over pi integral pi over 3 to pi over 2 cosine of u. All right, so now it's a lot of self-talk. Whose derivative are you staring at? I know you're thinking sine, but are you thinking positive sine or negative sine? And that's the part that got a lot of us on the test last week. It was just nonsense missing these negatives. All right, go with what you think it is. Maybe you think it's negative sine. All right, take its derivative. Are you staring at its derivative? No. The derivative of sine is cosine, so I want a positive sign here. All right, take the 2 seconds and take its derivative. We don't want to see any more ugly mistakes next time. And I've got my pi over 3 to pi over 2. All right, that's just a positive. I'm going to get that out of there so I don't think it's a t or anything. Again, I'm going to leave this 12 over pi out front, and I'm going to substitute in the sign of pi over 2 minus the sign of pi over 3. And this is called that first fundamental theorem of calculus. All right, picture 90. I'm picturing the sine curve. The sine of 90 is 1 minus the sine of pi over 3. I'm actually thinking the sine of 60, radical 3 over 2. And I've got this 12 over pi out front. I'm going to scratch this 1 and really call it 2 over 2. So I've got 12 over pi times 2 minus radical 3 all over 2. And if I want to multiply the 12 through, I'm just matching up my choices now. I'm going to say that's 24. Whoops, I lied. I'm going to say this 2 goes into 12 6 times. So I'm going to say that's 12 minus 6 radical 3 all over pi. All right, our next little section is a reminder about even and odd functions, and they come in pretty handy in integration. So there's 2 rules. If f is even, then the integral from negative to positive a. Notice those are the same number, just one's negative and one's positive. They cannot be different. So from negative 2 to positive 2, from negative 10 to positive 10 of f of x, it's really the same thing as saying you have 2 times the integral from 0 to a of f of x dx. And if f is odd, then when you integrate from negative a to a, again, they have to be the same number, one's negative, one's positive, of f of x dx, you get 0. So let's just kind of, slow down and talk about evens and odds again once you have those 2 rules written down. Let's pick probably your favorite even function, okay? Everybody has one. I'll tell you mine. My favorite even function is just x squared. All right, there's something I know the shape that it looks like. It has an even power, x squared. And when I think about x squared, I know that even functions are symmetric to the y-axis. Okay, something that's easily forgotten there, but let's be smart about. Even functions are symmetric to the y-axis. Now, let's just kind of review that rule from even functions from our pre-calc days. We said if f of negative x equals f of x, you have an even function. So if you substitute in negative x and you get the original out, you know your function's even. So let's play that game with this function. If I say f of negative x equals negative x squared, I get x squared, which is my original function. Hence, this is an even function. Now watch this. Let's say I integrate from negative 4 to positive 4. Would you agree those areas are the exact same? Yes. So that's why this rule says, okay, just say you have two of them from 0 to whatever that number is. It's the same thing as integrating from negative to positive 4. Same idea for the odd functions, except the rule's obviously a little different. Let's say you have an odd function, and again, you can pick your favorite. I'll remind you of mine. Perhaps you know it. Mine is x cubed. It's pretty simple, odd exponent. Nothing too crazy. And this one, notice the O for odd, is symmetric, you'll recall, to the origin. And I'm going to sketch out my x cubed function. I know it looks like this, a little concave down, concave up action. And now watch this. If I go from negative 4 to positive 4, remember those numbers have to be the same, what do you notice about that area to the curve and that area to the curve? Well, they're the same, but this one's below, so it's negative area, and this one's above, so it's positive area, so I know I'm going to get an area of 0. Okay, so it helps if you know if your function's even or odd, and again, that really only helps if the bounds are the same. Just to review that rule, of course, when you substitute negative x in, very similar to the even rule, this time you get out the negative f of x function. And again, I'll just show it to you here. If I substitute negative x into that function, I get negative x cubed, which is negative x. It is the negative version of that. Okay? Now again, I'm only using this trick if I notice my bounds are the same. So here's a quick example. Let's say we want to integrate from negative 3 to positive 3 of x squared times x to the 4th plus 1. Okay, now I'm only thinking maybe use the even and odd rule only because these bounds are obviously the same, but one's negative. All right, so my first instinct is to clean this up. So I'm going to say negative 3 to 3. That's going to get me x to the 6th plus x squared. Now, perhaps you don't know if that function's even or odd. All right, well, just plug in negative x and see what happens. If you find f of negative x, I'm going to get negative x to the 6th, which is x to the 6th, plus negative x squared, which is x to the squared. I get the same thing, so I know I have an even function, okay, which means I'm symmetric to the y-axis. So I can really say, I can just do the integral 2 from 0 to 3 of x to the 6th plus x squared dx. Now you might be saying, well, you still have to integrate and plug the bounds, and why is that beneficial? But if you're not in love with the number 0, hopefully by today you will become in love with the number 0. Plugging 0 in is so much easier than plugging in negative 3. Okay, and that's one main reason we try to find, if we can rewrite it. Let me show you one more example here. Let's say we integrate from negative to positive 4 of x divided by the square root of x squared plus 1 dx. All right, so again, this is only popping in my head because I see bounds that are the same. So I'm testing for even and odd just to save some time. So I'm going to substitute in negative x and see what I get. On top, I get negative x. On the bottom, if I square that, I just get the same thing, x squared plus 1. Would you say this is the same function or the negated version of the function? Well, basically, would you say this is the same thing as saying negative x over the square root of x plus 1? Basically, I'm taking this function and slapping a negative in front, so it's the negated version. Hence, I have an odd function. And since I'm odd, I'm symmetric to the origin, which means I can say this is really, whoops, I don't even need to integrate again. Because it's odd, I can say my answer right off the bat is 0. Okay? So it really helps sometimes to know if you have an even or an odd function. It saves you a lot of time. Well, the main thing I wanted you to get from tonight is really focusing on changing those bounds into terms of u. So we'll get a lot of practice tomorrow. Have a great night.